This webcast deals with work and how you get the quantity work, which is a measure of energy. Oftentimes, work is defined as a force times a distance, where the force and the distance act in the same direction. And you just take the magnitude of the force times the magnitude of the distance. That assumes that the force and the distance in the same direction and they're constant and in a straight line. Earlier in this class, we learned what do you do if the force acts one way and the displacement acts a different direction. And in that case, the work is found by taking the force vector and the direction vector and dotting them, which in statics you'll often use as the magnitude of the force vector, the magnitude of the direction vector times the cosine of the angle between them. In this class, right now, what we're going to do is to develop a formula which allows you to use this quantity in any situation. This situation still assumes that the force is constant and the displacement's in a straight line, but rarely will your forces be constant and rarely will the displacement always be in a straight line. So what if you're dealing with a force field where the vectors are not constant at all, and they're changing based on where you're at, and the displacement is not in a straight line, and you move around some kind of different path? Well, the idea is cut the path up into a bunch of little pieces. On one of those pieces, you can approximate it by essentially a straight line. Well, that straight line gives you your straight distance. But then I also need the force, but the force may not be the same along this line. But if I cut the segments up small enough, if I cut the segments up tiny enough, then along one of those thin lines, the force doesn't change very much. So what we do is we take an almost constant force, and we times it by a almost straight distance, or in this case we're going to approximate it with a straight distance. To get that distance, well, its length is ds, and it essentially moves in the tangential direction. So this right here is our displacement vector, and our force is almost constant. And if I do that on a little curve, I get a little amount of work. If I want to find total work, I add up the little amounts of work, which means I add up the force dot the tangent vector ds. This is now a line integral. If I want to compute this integral, then t is found by taking r prime over the magnitude of r prime. And remember, ds is your r prime speed times dt. Now I've got bounds a to b since I'm integrating with respect to t, but notice that the magnitudes of the velocity cancel. And we are just left with the integral from a to b of f dot r prime dt. This is the formula used to compute work. Oftentimes it's abbreviated as follows. Rather than writing r prime dt, if we look at dr dt, and note that dr dt is also written as r prime, you can multiply both sides by dt to just get dr is r prime dt. So in differential notation, people often write work is f dot dr. Another way to actually write work is if your vector field is given by m, n, p, and your curve is given by x, y, z, then the derivative of the curve is dx, dy, dz, and then I guess it'd actually be dr. We've left the dt's off everything. Well then, if I take f and dot it with dr, I just need to dot these two, which means it's m dx plus n dy plus p dz. And that is another formula used for calculating work. If you're in 2 dimensions, you just get rid of the third component. And now we have formulas for work. All three of these formulas essentially give you the same idea. This is the one we always have to resort to do the computations, but these are alternate ways of writing work, just to get an idea of what's going on. We're now going to look at an example. The example is we're going to look at a spin field, minus yx, and we're going to look at a curve whose it's a circle of radius 3, so 3 cosine t, 3 sine t, and in order to go all the way around the circle, t has to go from 0 to 2 pi. So my vector field is the vector field which is spinning things around in a counterclockwise fashion. And my curve is a circle of radius 3. Notice that as I move along the circle, the forces are actually pointing in the direction in which I'm moving. I had to get a positive amount of work because as I'm moving along, every time I move along, my tangent vector and the force vector happen to be in the same direction, which means that when I take F and dot it with T, I'm going to get a positive number. And I'm going to be adding up positive numbers all along the curve. So what we're going to do is actually just carry out the computations. The idea is I've got to calculate R prime. R prime is minus 3 sine t, 3 cosine t. Here's my x value, here's my y value, here's my dx value, here's my dy value. I need m. Well, this is m, and that's n. But I'm going to rewrite these in terms of t. So I'm going to write f in terms of t now. I'm going to replace the y as 3 sine t, so this is negative 3 sine t from right there. And then I need a comma, and x is 3 cosine t. So now, if I want to find work is found by taking f and dotting it with dr. Well, that's just taking these two things and dotting them. So if I dot those, I end up with negative 3 times negative 3 is 9 sine squared t, and then I get plus, now let's take that times that, which is 9 cosine squared t. I'm going to integrate that from 0 to 2 pi dt, and many of you probably already noticed that this is 9 times 1. 9 times sine squared plus cosine squared. 0 to 2 pi dt. Now this integral right here is I'm just integrating something, and the height is 9, and I'm going from 0 to 2 pi. So the area of this region is 9 times 2 pi, which is 18 pi. And that completes this